Imagine walking into a library where every book lies scattered in a chaotic pile. A traditional programmer would just draft a strict rulebook. You check the cover for red and numbers, then file it in the science section. Spot a book with cat photos, just toss it in the pet section. That rule runs smoothly until someone walks in with an underwater basket weaving manual the system never covers. Ditch the rulebook. Show the computer thousands of examples of sorted books and tell it to figure out the patterns yourself. It studies the patterns, builds internal rules, and applies them instantly. Machine learning flips the script. It just learns to handle brand new books it has never seen before. The core idea is learning from examples instead of explicit instructions. Every machine learning system runs on one repeating cycle. It grabs data, learns from mistakes, and constantly improves. You feed the machine raw examples, photos, text, sensor readings, basically anything you can actually measure. The system builds a mathematical model. It is simply a function that maps your inputs straight to an output. Think of it as a wild guess. The system compares that guess to the right answer. The difference is your loss or error. The system tweaks its internal parameters to shrink that error. Then it tries again. It repeats this millions of times until the loss drops to almost nothing. Once trained, the model faces completely new data. It makes a prediction. Then the whole loop starts over. It is basically iterative feedback. The system improves with every training round, just like a person practicing a skill. This is where the magic happens. The confusion starts right alongside it. Traditional programming follows a rigid workflow. You map out the steps first. The programmer writes every single rule. The computer just executes them. The computer discovers the rules by studying input and output pairs. The programmer supplies the data and the learning framework. The actual logic emerges straight from the training. Traditional programming asks what rules turn input into output, while machine learning hunts for data patterns that link them together. Both methods work brilliantly. You are simply solving completely different kinds of problems. Neural networks power nearly every modern machine learning breakthrough. That organic-sounding name is just a disguise for heavy mathematics. Picture a neural network as a relay race of mathematical layers. Each stage handles a single focused task. The input layer takes in raw data like a pixel, a word, or a sensor reading. Hidden layers transform that information by pulling out key features. Layer 1 might simply spot image edges. Layer 2 stitches edges into shapes, while Layer 3 weaves those shapes into faces. The final output layer then delivers the verdict. It spells out if you are looking at a cat, a fraudulent transaction, or a high-risk patient. Every neuron connection carries a weight that dictates its importance. Training constantly tweaks those numbers to crush the error rate. That is the entire process. No consciousness, no magic. It is just weighted math repeated at lightning speed across massive datasets. You have likely heard the term. It powers the image generators dominating headlines every week. A diffusion model operates in two distinct phases. Forward diffusion starts with a real image and slowly injects noise until it becomes pure static. This corruption process is completely fixed and known. Reverse diffusion flips the script by training a neural network to undo that noise step by step. The network learns to look at a noisy picture and predict exactly what it looked like, one step cleaner. Once training finishes, you start with pure static and run the whole process backward. Watch the model strip away the static one layer at a time and poof, you get a fully coherent image. The real trick is that the model learns the hidden patterns of real photos, like what makes a face look human or a landscape feel grounded. It never copies existing work. It synthesizes entirely new ones. Imagine you work at a bank and someone swipes a card in London at 2 p.m. Then the exact same card hits Tokyo at 3 p.m. That travel speed is physically impossible. A traditional programmer writes a straightforward rule. If two transactions are over 5,000 miles apart and happen within 2 hours, you flag it. That logic works perfectly until it only catches that single pattern. A machine learning model watches every single transaction. It tracks the time and amount and location and merchant type alongside your entire card history. That system quickly spots which combinations look normal and which look completely wrong. It might flag $15 for a coffee in Tokyo as suspicious. That specific cardholder never buys coffee before noon. This catches every detail a hard-coded rule would miss because it sees the full picture. Machine learning learns patterns directly from data instead of relying on written rules. Every system follows the exact same loop. You feed raw data into a model and measure loss, then run training before predicting. Neural networks stack chained layers of weighted math to extract features automatically. Diffusion models take a different approach by learning to reverse a noise process. That lets them generate images from pure randomness. Traditional programming and ML are a perfect pair. One writes the rules while the other discovers them. If that made it click, subscribe. We break down the frontier of tech and AI every day.